breaking the wall of life's origin. How toxic molecules enabled the formation of RNA and early life. John Sutherland, Medical Research Council Laboratory of Molecular Biology.
On November 9th, 1989, I was getting ready to apply for my first independent academic position.
Thank you, everybody. That is a difficult act to follow. I've been upstaged many a time in my life, but never by a tree like that. So what I'd like to do is to talk to you a little bit about two big questions. These questions relate to life. The first is, how did we get here? You know, are we alone? How did we get here? How did life start on Earth, and does life exist elsewhere in the universe? And of course, when I talk about how did we get here, I'm not talking about getting a taxi from the beautiful new airport up the road there. I'm talking about how chemistry on the early Earth might have given rise to life. It's an intriguing question, one we've been working on for a while. And I'm going to call this talk basically The Origin of Life on Earth Out of the Blue, and you'll see why as I get to the end of the talk. So, of course, people have been thinking about this sort of thing for a long, long time. Humans have always wondered where they came from. And the way we think is naturally reductive. And so people in the past, in the 15th and 16th century, for example, started taking humans, normally dead humans, and dissecting them. And by dissecting them, they could work out how the various subsystems within the body worked. And so you have here some beautiful illustrations of various subsystems, the reproductive subsystem, the alimentary canal, the musculature and skeletal subsystem, and the skin. And you can imagine people at the time wondering, basically, when they did these dissections, you know, this is an inordinately complex system, the body. You know, how did it arise? Look at all these different bits, each of which is important for life. Which of them came first? You can't imagine the whole thing coming first. Something must have come first. And so you had people, basically, you can imagine the conversations. Well, the reproductive system must have come first. We all know that's supremely important. And other people saying, without food, forget it, you know? Or without muscles to get you to where you want to be to eat or to reproduce, you can also forget it. And without the skin to protect you and to keep everything sort of as part of the body, again, what do you do? So people were confronted with an inordinate problem, this complex situation. How do you actually sort of imagine how it could arise? And you had to wait a while before people actually realized that the solution lay in the fact that these are organisms which have evolved from simpler precursors. And so by phylogenetic analysis, you can reduce these things in complexity, and you can see how historically they arose from simpler organisms. And ultimately, you get back to the point where you can see that all life on Earth is rooted in single cells. We think of this as the last universal common ancestor, either a single cell or communities of cells, and all of that has given rise by historical evolution to the things we see around us, the biological systems we see around us. But then molecular scientists later on start looking at this and they say, well, hang on just a minute, you know, when I start looking at this from a molecular perspective, this actually looks really complicated again, because you can't imagine a cell without informational molecules. You have to have some sort of information you can have to program what's going on in biology and also to pass the information from one generation to the next. But that's not enough. You also need to have something to catalyze, something to accelerate the processes that are going on in the cell, to make them happen faster and more efficiently. There's not much point doing any of that unless you're compartmentalized. For example, if you innovate, you know, biologically speaking, if you innovate, of course, you don't want to share that innovation with your competitors. You want to keep it to yourself. And so compartmentalization enables you to do that. And finally, you need building blocks and energy if you want to do anything. You need to provide energy to drive the system, and you need to get the sort of material wherewithal to make things. And so what people are doing in the molecular sense is doing exactly what the 15th and 16th century people were doing when they were dissecting bodies. They're looking at the cell and they're saying, well, in fact, the cell itself is just too complex. It's too difficult to imagine all of that coming into being in one go. How did it start? Where did it come from? In other words, the problem reduces in a chemical sense to the fact that trying to imagine how chemistry could have produced all the individual components required to start life is just putting too big a challenge in front of the chemists who are trying to recreate this, trying to imagine how it could have taken place on Earth. Surely you need different chemistries to make the various bits and pieces. Amino acids, nucleotides, lipids, all the different components of the cell. It was imagined that you would need different chemistry to make all of those different bits and pieces. And surely if you tried to operate all those chemistries at the same time, you would get what anybody who has worked in a chemistry lab has made before, which is just an intractable brown mess. Okay? There are quite a few people who have obviously done some chemistry here. Okay? My own sort of efforts in chemistry were probably even less successful. Okay? Practical chemistry. But these are assumptions, and these have always been assumptions until the last few decades, when people have started to investigate this by comprehensive experimental investigation. And so there are people who would say, look, too complex, and so we've got to start somewhere. Why don't we start with one or other of these subsystems? So there are some people who say, look, information is more important than everything else, so let's posit that informational molecules came first. There are others who say, no, information's too complex. You can't do anything without catalysis. Let's have that. And of course, you can guess the rest. Other people who said without compartments first. And so the field became polarized, quadrupolarized, different people recognizing different attributes, all recognizing that it was too complex to imagine everything coming together at one point, but then all agreeing that something must have come first, but then differing in terms of what they thought might have come first based upon their predilections, their education, and so on, their bias. And that's kind of the point at which we got into this, because we were thinking about informational molecules. But we did have it in mind that a more holistic approach would be required than this sort of simple reductionist approach, because the reductionist approach was suffering from the fact that all of those four groups of people were all making good points. Yes, you do need informational molecules. Yes, you do need building blocks. You do need energy. You do need compartmentalization. You do need catalysis. So how do we reconcile these issues? So we started thinking about informational molecules, and we were attracted to this beautiful informational molecule, RNA, which I've shown with Jim Darnell's book cover illustration as a transition from an inorganic material, a stone staircase, into an organic structure, with the indication that if you can achieve that, the sky is the limit. Okay? So can we get from very, very simple precursor chemicals, the stone staircase, to complex organic structures? If we can, the sky is the limit. So I know it's Sunday morning, and I apologize for putting chemical structures on the slide. I will not leave them on for too long, but they will come back. Let me replace that chemical structure, which is a chain of repeating units. Okay, it's a string of beads for those of you who are not inclined to think about molecules on a Sunday morning. Let me represent it with a cartoon. And one of the things that held the field back was the fact that this cartoon reveals that the constitution of the building block, the repeating unit of the informational nucleic acids, is actually a red bit, a blue bit, and a purple bit. Okay? The red bits are sugar, the blue bits are nucleobase, the purple bit is phosphate. You learn about those in different lecture courses. Ribose you learn about in carbohydrate lecture courses, nucleobases in heterocyclic chemistry courses, and phosphate in inorganic chemistry courses. And if I had been a diligent student, I would have attended inorganic chemistry courses. As an organic chemist in Oxford, back in the day, I didn't, which was, in retrospect, a mistake. But c'est la vie. So the cartoon, when you look at it that way, it basically cues in your mind a way of trying to make it. Chemists are always trying to imagine how things could have been made or how they could be made. If you've got a blue bit, a red bit, and a purple bit, how do you make that? Well, obviously, you make it by making a red bit, a blue bit, and a purple bit, and you try and join them together. And people had tried to do that for some 50 years, and it just didn't work. And so that gave people the idea that, oh, you can't join the preformed bits, doesn't work. Can't have had informational molecules, something else must have started the origin of life. That, I think, is a premature conclusion. And we thought that was a premature conclusion, so we started investigating it. And the idea was, let's not start with preformed bits. Let's start with half a nucleobase, half a sugar. The purple bit helps those join together. We can then add the second half of the sugar. We can then add the second half of the nuclear base, and we can finally incorporate the purple bit. So it's basically saying you can make things not by preforming the components, but you can assemble the components together. Now, I have a plan here to stop Klaus interrupting me with his throat clearing. So I'm going to invite him on the stage and give him a hug. Klaus, I would like to hug you. Let us hug. This is a preformed hug. And it doesn't work. What do we do? Thank you, Klaus. That was a good hug. He is, I believe, what you call the strong silent type. So there are other ways of solving problems in chemistry. So how do we go beyond that? Well, we've got to make those building blocks from something smaller. Hydrogen cyanide is where we want to start. It's a very fundamental molecule in origin of life chemistry. Turns out we can turn it into this smaller red bit. We can join red bits and blue bits. We can then assemble half sugars. We can assemble other halves of sugars. So we can do chemistry by taking hydrogen cyanide, reducing it, and turning it into the sugar building blocks. You don't need to know the details. What you need to know is that if you do that and iterate it, you can make a huge collection of molecules, which happens to correspond almost precisely to about half of the molecules you need to kickstart biology. Okay? Sorry, the molecules you need to kickstart biology, it's about half the molecules you find in basic rudimentary primary metabolism. Half the amino acids, nucleotides, and lipids. We can obtain the feedstocks on an early planet by atmospheric chemistry after impacts, which reduces the atmosphere. And we envisage this sort of chemistry advancing in terms of complexity and indeed in the degree to which the system is alive. We don't believe in a progressive increase in complexity followed by a Frankenstein's monster moment where things suddenly become alive. We think that the various attributes which collectively constitute the living state can be acquired progressively and sequentially, and thereby you can proceed in a series of stages towards becoming alive. So there are intermediate stages of aliveness. So somewhere below that dashed line that you think of as being alive is that Berlin taxi driver who didn't get me to my hotel until almost midnight last night. Okay? There are clues that come out of this as well. So, for example, we find that the amino acids we can make by reductive hydrogen cyanide chemistry happen to correspond to half the positions in the genetic code, and they're those positions in the genetic code which are characterized as family boxes. They're boxes in the genetic code where the nature of the third base of the codon doesn't differentiate the amino acids that's coded. That, it turns out, is a huge clue. So fundamental chemistry can clue you about the structure of biology, the central dogma of biology. Chemistry doesn't just get to a certain point and then hand over to biology. Chemistry is pervasive. It reaches all the way up into the central dogma of biology. Okay? Chemistry is a powerful subject. We're in Berlin, and I've talked about the origin of life out of the blue. Why out of the blue? Well, it's because hydrogen cyanide, Blausauer in German, it dates back to the historical times in Berlin when people were trying to make pigments, red pigments. But they found that if there were contaminations in the materials they used, they got ferric ferrocyanide, a blue cyanide-containing metal complex, which they discovered could be used. And here's a picture from an art gallery up the road there. That can be used to produce a beautiful blue color in pictures. And people from that blue color, by heating it, they isolated this blue acid because it derives from a blue pigment. Blausauer is hydrogen cyanide. And hydrogen cyanide was then purified by French researchers, Monsieur Gay-Lussac in Paris. And I just leave you at this stage with a comment about what did Gay-Lussac say. He said, prussic acid, which of course was the French way of describing Blausauer, blue acid. Prussic acid, prepared as I've just described, has the following properties. It's a colorless liquid, it's very smelly, it's got a fresh taste. My God! A fresh taste. it paralyzes you, and it's a veritable poison. He survived. Anyway, so the life on Earth is the origin of life out of the blue. What about life elsewhere? Doesn't have to be blue. It could derive from being red, maybe, for example. So I'd like to ask you if you could pick from underneath your chairs just one of the 3 cubes you find there. And with Klaus's help, we're going to do an experiment which relates to the probability of life starting on an exoplanet. There are 10 to the 22 stars out there. On average, each one has a planet. My astronomer friends tell me it's a huge number. I say, that's not even a mole of planets. Chemistry, remember, is a powerful subject. But anyway, the experiment we're going to do is to try and connect these red cubes you've got, which is chemistry, with an exoplanet. And actually, secretly, I'm recruiting for the English cricket team. So if anybody can get their red cube, I'm going to count to 3. And on the count of 3, if you could throw your red cubes and try and get them in this basket, I'm going to do it too. That would be great. So after 3, 1, 2, 3. So, is there life elsewhere? There is life elsewhere. Even without Klaus's sleight of the hand, there was life out there. Thank you very much.